So, finishing off Chapter 21 with a discussion of hemodynamics and the factors affecting blood flow. Blood flow itself is most affected by two factors. Number one, we have to give blood a reason to flow. Well, that reason to flow is, of course, the pumping action of the heart. In this case, it directly relates back to cardiac output. Cardiac output, of course, is the volume of blood ejected from the heart per minute. And the amount of blood and the pressure behind that force creates the blood pressure that forces the blood through our blood vessels. But like anything that has to move through or across any type of area, there's going to be some type of resistance to flow. Resistance is going to be created or be a side effect of friction. This friction is created when the blood rubs against the vessel wall. Now, this resistance is going to, or the amount of resistance the blood has to overcome in order to get to all areas of the body, is going to directly relate to the amount of pressure that needs to be exerted. For example, if you're driving your car and you go ahead and take your foot off the gas, your car will coast a certain distance, but it won't keep going forever, because as the tires interact with the road, friction is created, and that eats up some of your force, some of your speed. The same is true for your heart. Okay, as your blood flows through your vessels further and further, this eats up some of that pressure, or the resistance that it encounters eats up some of that pressure, so as we get further and further from the heart, the pressure falls. We saw this when we looked at the capillaries, right? When we got to the capillaries, we only had a pressure of 35 left, when we started out with a maximum of 120. So what we see is these two are going to be directly related to each other, because the amount of pressure you start out with, X, has to be proportional to the amount of resistance that it has ahead of it. So if you have a higher resistance ahead of it, then you need more pressure to overcome it. Now, what we see is these are the two primary factors that influence blood hemodynamics and blood perfusion. But in addition to these two factors, there are other things that may come into play, and that includes velocity, volume, and venous return. Velocity, so we'll talk about each of these on the following slides. Starting first with friction. As I mentioned, friction is experienced when the blood rubs up against the vessel wall. Now, we've done our best to minimize this when we've used our simple squamous epithelium, and we've smoothed out that vessel wall as best as possible, but we can't get rid of it completely. Now, there are several factors that can affect your viscosity, your resistance. And some of these factors you're stuck with. Some of them we can adjust when necessary. Let's start out first by talking about viscosity. Viscosity relates back to the thickness of your blood. And thickness of the blood is primarily related to the number of formed elements, which, as you will learn in Chapter 19, pretty much refers to all the cells that are present in the blood. The more cells present in the blood, the thicker the blood. The harder it is to push it through your blood vessels. This can be demonstrated if you've ever drank a milkshake through a straw versus drank a Coke through a straw. It's much harder to suck that milkshake up through the straw, and as a result, you must create more force in order to accomplish that. Total blood vessel length will also increase with increased resistance. So longer blood vessels have higher resistance. Now, this analogy can be demonstrated for example, when you're driving a car. If you want your car to coast a certain distance, And you start out with, you have to exert a specific amount of force or pressure to get it that distance. And the longer you want that car to coast, the more force or speed you have to start out with to ensure that it coasts to where you want it to get to. Now, keep in mind, this is your total blood vessel length. This idea of, having longer blood vessels in taller individuals, oh, well, they must have, higher pressure. That is not what we're referencing here. What we're referencing, or what we're saying, is that if we take all of the blood vessels in your body and add them up from end to end, that is what we're referencing with total blood vessel length. This is best demonstrated with individuals that are obese, because in obese individuals, you have extra blood vessels for every pound of fat. So those extra blood vessels add to your total blood vessel length, and as a result, cause many obese individuals to suffer from hypertension. Now, of all of these things, for most part, you really don't have much to deal with viscosity. That's not something you can easily change. And you also really can't change blood vessel lengths, at least not without losing weight. We can't just decide to cut off blood flow to blood vessels X, Y, and Z, because obviously the tissue would die. But what we do have control over, and what we do manipulate in order to regulate resistance when necessary, is blood vessel diameter. Now, when we look at blood vessel diameter, this is what we see. If we take your average vessel, or two vessels, we see we have a diameter like that, and a diameter like that. Well, the larger one will have less resistance than the smaller one, and here's why. If we think about it, the larger one has less blood in contact with the vessel wall compared to everything that's free-flowing in the middle. If the blood is free-flowing in the middle, then it's not touching your it's not touching your vessel walls, and as a result, not causing any type of resistance. Whereas this small guy over here, more blood is in contact with the vessel wall, less is free-flowing, so this one is going to have higher resistance compared to this one that's going to have lower resistance. So the smaller the vessel, the higher the resistance. Again, you can think about, taking a drink of your Coke through a coffee straw, a very teeny tiny coffee straw, versus a regular drink straw. It's much harder to suck things up through smaller straws. Now, not only does this cause the resistance to go up the further you get from the heart, because vessels get smaller and smaller, but this also is something that we can adjust when necessary. So if we want to manipulate our resistance, we do so by adjusting blood vessel diameter via vasoconstriction or vasodilation. This change in resistance can help us, particularly when we're trying to make it easier to perfuse or send blood to areas that are particularly in need of blood. We can manipulate or adjust this blood vessel diameter in order to adjust blood flow to that area, which becomes very important, as you will see shortly. Now, there isn't any one factor that we deal with when looking at resistance. In actuality, all of these factors play a role. So what we end up doing is adding up the total resistance factors for your individual physiology, and we get a general resistance idea of systemic vascular resistance, which is the sum total of all of these resistance factors. Now, your book calls it SVR, or systemic vascular resistance, but you also sometimes might hear it referred to as total peripheral resistance. And again, this is just the sum total of all of these resistance factors, and your total peripheral resistance is directly related to the amount of force that needs to be exerted in order to overcome these issues. Now, as I mentioned, we do have a limited ability to adjust resistance as needed, and that relates directly back to controlling blood vessel diameter via vasoconstriction and vasodilation. Now, technically, all blood vessels except capillaries have the ability to vasoconstrict and vasodilate, but if we want to adjust resistance, associated resistance, and get the biggest bang for our buck, we're going to do this at the arterial level, because we can make very minor changes to massive numbers of arterioles and get an easy and get the results we needed, the changes in resistance we needed with the least amount of effort. Now, again, the amount of effort we need to start out with directly relates to the amount of resistance. So if we have a specific resistance factor, then we need to start out with a specific pressure. Now, pressure is the force exerted by your heart. And in technicality, blood pressure, or what we learned earlier, we renamed as blood hydrostatic pressure. Same thing. Is the pressure of your blood pushing on the vessel walls. This entirely originates from the contracting efforts of the ventricles of the heart. Now, the further we get away from the heart, this pressure begins to fall. And again, this is because resistance is eating away at that pressure as we get further and further from the heart. Now, since your heart does not stay in a contracted state permanently, it alternates between a contracted and relaxed state. What you see is when you're closer to the heart in your large arteries and even in some of your arterioles, you're actually going to see a fluctuation. Remembering that the max pressure your heart exerts is your systolic pressure, and that's the pressure exerted when your heart is in a contracted state, whereas your diastolic pressure is the pressure your heart exerts, or the pressure left over when your heart switches to a relaxed state. Now, this fluctuation continues, but it diminishes. The degree of fluctuation gets smaller and smaller the further we get away from the heart. Okay. Now, with this changing pressure relationship, what we end up looking at when we want to look at the blood pressure in your body, we don't necessarily look at the pressure exerted by the heart directly, because that doesn't give us as much information as we need, because the pressure exerted by the heart doesn't necessarily give us a value for, okay, is this going to be enough to overcome all of the resistance? This is when we start talking about mean arterial pressure. Mean arterial pressure takes into account not only the resistance, not only the force from the heart being cardiac output, but also resistance that might come into play. Now, mean arterial pressure is the average pressure within your arteries, taking into account contraction and relaxation of the heart, as well as TPR. Now, the technical equation for MAP is cardiac output times TPR. Now, this makes sense, right? Because mean arterial pressure had to take into account not only the force the heart is exerting, but the resistance that the heart that we have to overcome. Now, in reality, in most individuals, we can't easily measure these two items, so we can't estimate TPR from your systolic and diastolic pressure. And we estimate MAP with the equation 1/3 systolic pressure plus 2/3 diastolic pressure. Now, the reason why we have this unequal relationship is that your heart spends more time in a relaxed state than it does in a contracted state. This is why we're only taking 1/3 of your systolic pressure and adding it to 2/3 of your diastolic pressure. Now, pressure itself is intimately linked to blood volume. Because remember, the pressure of the blood exerts against the walls of the vessel. Well, I guess blood was over here. Didn't need that. But if we all of a sudden get rid of some of the blood, well, there's less stuff to exert against the vessel wall. And this less stuff, so to speak, causes a decrease in your overall pressure. Not only does a drop in blood volume cause blood pressure to drop, but this also becomes a method of regulating blood pressure, as you saw when we looked at the hormones, how a great variety of those hormones targeted blood volume in order to fix problems with blood pressure. Now, I also mentioned that blood velocity played a role in blood pressure regulation. Now, I want you guys to think about what the ultimate goal of your blood vessels and the blood within them. So with the velocity of blood flow, if blood is flowing too quickly through those capillaries, then we're not going to have adequate time to exchange what's necessary. Either we're going to miss something getting dropped off, or we're not going to be able to grab something that needs to get picked up. So with velocity of flow, this becomes extremely important. Now, velocity of flow is the speed at which blood flows through your vessels, and it is inversely related to the total cross-sectional area. Now, what ends up happening is the total cross-sectional area, as you see by this graph, increases the further we get from the heart. This means since the total cross-sectional area is increasing, that means velocity is decreasing. Now this is exactly what we want, since by the time we get to the capillaries, we want things flowing as slowly as possible in order to have adequate exchange taking place. Now, as we start going back to the heart, cross-sectional area goes back down again as all those vessels join into one, which means velocity is going to start going up, which of course helps us get that blood back to the heart. Venous return. Now, we're of course pumping blood out of the heart, and getting it out to your tissues. Okay. But the continued function of the heart relies on the fact that the blood continues to get back to the heart. But if you recall, when we were leaving your capillaries after capillary exchange, our systemic blood pressure was down to 16 millimeters of mercury. Yet we started out at 120. So we went from 120 to 16 just to get us to the capillaries. Now all we have left is 16 to get us back to the heart. That doesn't seem like a lot. Well, we better have some established mechanisms in place in order to help get this blood back to the heart. In this case, we have two primary mechanisms. We have skeletal muscle pumping and respiratory pumping. In the case of skeletal muscle pumping, your veins are strategically placed between muscle groups. So every time a muscle group contracts, this belly shortens and gets wider. Well, as the belly of the muscle widens, it compresses the veins, forcing blood upward. Now, problem is, when the muscle relaxes, blood's going to want to go back down again. Well, we want to prevent that because we don't want to lose what little effort we gained. So we prevent that with those lovely valves, which are characteristic of blood of all veins. Now, skeletal muscle pumping helps us in our limbs. But once we get out of our limbs, particularly our legs, once we get out of our limbs, we're in our abdominal, pelvic, and thoracic cavity. Well, then what do? Well, remember, blood always flows from an area of high pressure to low pressure. Well, if this is the case and we need to get blood back to the heart, we have two options. We either need to make the pressure in our abdominal pelvic cavity higher or the pressure in our thoracic cavity lower. Well, we choose, or our body uses, the second option. And it does this when it relies on breathing. Every time you inhale, the pressure in the thoracic cavity drops. Now, this drop in thoracic pressure is there in order to suck air into your lungs, but at the same time this drop in pressure is sucking air into our lungs. It also acts to suck, so to speak, blood up from the abdomen. Okay, so this respiratory pump helps suck the blood from the lower pressure areas in our abdomen. Of course, when we exhale, the pressure goes up again, and you would think blood goes back down. But again, we use these same valves to prevent the backflow when the pressure gradient is being manipulated. So let's see if we have some questions here that see how well you guys are following along. Again, pause if necessary as you work through these and see what you come up with. So, which statement is not true, reading carefully, of the hemodynamics of blood flow? Systolic pressure is the highest pressure in an artery. An increase in lumen size increases blood flow. Total peripheral resistance is controlled by arterioles. A decrease in lumen diameter decreases blood pressure. And finally, diastole is the interval between heartbeats. Well, of all of these, the only one that is not true is D. In order to make D true, we would have to cross out decrease and write increase, because remember, a decrease in lumen diameter results from vasoconstriction. And anytime you vasoconstrict, blood pressure goes up. Next question. Pause if necessary as you guys think about this. Which of the following is not considered a factor in vascular resistance? Vessel length, viscosity, pH, diameter of your blood vessel, brainstem control of peripheral resistance. Well, the only one that has nothing to do with resistance is blood pH. All the rest do. Which of the following would result in a decrease in peripheral resistance? So a decrease in TPR. Increase in vessel length, increase in blood viscosity, decrease in vessel diameter, or vasodilation. Now, most students struggle with these two here because they realize the relationship between the two. Well, let me see if I rewrite these for you. Vasodilation equals an increase in vessel diameter, whereas a decrease in vessel diameter equals vasoconstriction. With the verbiage change, does it make your answer easier to identify? Hopefully it does, because the correct answer is D. Vasodilation results in an increase in vessel diameter, so a decrease in peripheral resistance. A lot of people think this one because they see the decrease, but they don't make the connection. So make sure you understand the relationship between increasing and decreasing vessel diameter as it relates to vasoconstriction and vasodilation. Again, giving you a lot of these not true questions. Which statement is not true of venous return to the heart? An incompetent tricuspid valve decreases venous return. Well, this one kind of goes back to the heart, since you got to think what the function of that tricuspid was for. When standing, the proximal and distal veins in the legs are open. The respiratory pump increases venous return to the left atrium. Milking refers to the contraction of the calf muscles to increase venous return. Venous return is generated by contraction of the left ventricle. So, going ahead, which one of these is not true? C. Respiratory pumping increases venous return to not the left atrium, but the right atrium. Okay. So, great. We know how we can target and affect blood vessel diameter, blood pressure, resistance. So how do we not only maintain blood flow, hemodynamics, and perfusion, but how do we know when we need to make adjustments? Well, that's of course going to come out of that cardiovascular center, the same center that we used in the heart for blood pressure heart rate regulation, also sends signals to your blood vessels. Now, like your heart, the cardiovascular center can receive signals from two general areas, from different parts of the brain, including the hypothalamus and higher brain centers, but also receives signals from those three main receptors that are spread throughout the body, monitoring the physiological state of your blood vessels and blood pressure. Those signals come in, and then out comes either parasympathetic or sympathetic stimulation. Now, I'm going to go through these three receptor types on a blank page, and I'm simply going to write that it either increases or decreases sympathetic, increases or decreases parasympathetic, but you need to know what that means. So if I say increase sympathetic, you need to know what that means in terms of both the heart and the vessels, as we see here. So let's go ahead and come to a blank screen and come up with this. So, as we saw, we have, we'll start with proprioceptors here. Proprioceptors are going to monitor joint position and body movement. Now, if we detect an increase in proprioceptor activity, this means we are about to start exercising, which means we're going to need to increase blood pressure to maintain perfusion. So this is going to, in terms of our blood vessels, going to result in an increase in sympathetic stimulation of your blood vessels. Now remember, in the heart, what we did is we wrote increase sympathetic / decrease parasympathetic. But remember, in your blood vessels, we only receive sympathetic stimulation. So by increasing sympathetic stimulation, we primarily get vasoconstriction. And by decreasing parasympathetic stimulation, we get our vasodilation. The opposite is true for a decrease in proprioceptor activity. This means your activity level has decreased. Well, if our activity level has decreased, our pressure doesn't need to be as high, so we decrease sympathetic stimulation to our blood vessels. Well, next let's do our chemoreceptors. Chemoreceptors, as you recall, monitor different chemicals in the blood, particularly oxygen, O2, CO2, and pH. So the two kind of ways in which chemoreceptors are activated: first, if we have a drop in O2, which typically corresponds to an increase in CO2 and at the same time a drop in pH. Well, this means we need to get that blood flowing more quickly. We need to help get that blood to our tissues. So this is going to result in an increase in blood pressure and an increase in sympathetic stimulation of our blood vessels. Vice versa, if we have an increase in O2, decrease in CO2, increase in pH, this results in a decrease in blood pressure, as we want to keep our blood from flowing and not get rid of our CO2 because we need it, and this results in a drop in sympathetic stimulation. Last but not least, we have the obvious one that's going to be regulating blood pressure and blood vessel diameter most frequently, which is your baroreceptors. Your baroreceptors are the receptors that directly monitor blood pressure. Now, you have only one type of baroreceptor. That means that one single baroreceptor type needs to be able to signal both high blood pressure and low blood pressure. In order to do that, your baroreceptors work very similarly to how our sympathetic system works. Your baroreceptors will actually send a signal, a constant signal rate to the cardiovascular center at rest. So at rest, they have a constant signal rate. So a constant number of action potentials being sent to the cardiovascular center. At that constant rate, the cardiovascular center ignores it. So if that signal is sent at its constant normal rate, the cardiovascular center recognizes this as normal and ignores it. Now what we do is we can either decrease or increase this rate in order to stimulate or signal to the cardiovascular center both high and low blood pressure. So if we have a high blood pressure problem, well, high blood pressure, the baroreceptors result in increasing signal rate, of our baroreceptors. This increase in signal rate is detected as an increase in blood pressure, which results in the need to vasodilate, which would mean a decrease in sympathetic signaling. Vice versa, if the problem was a decrease in blood pressure, this would cause the baroreceptors to decrease their signal rate, which would result in an increase in sympathetic signaling, as we need to vasoconstrict in order to bring that blood pressure back to normal. Now this is seen here, and again, remember, I simply said increase sympathetic, decrease sympathetic, etc., but you then need to know what that means, okay? So make sure you kind of extend that out and don't just write increase sympathetic, decrease sympathetic, but in your notes, write it out. What does it mean to be increased sympathetic? What does it mean to be increased parasympathetic? So on and so forth. Now, elaborating on the baroreceptor reflex that we just talked about, baroreceptors are generally found in two different regions of the blood vessels, or two different regions of your body. There, that's the word I'm looking for. You have baroreceptors located within the carotid sinus. The carotid sinus is the slight expansion in the common carotid artery right before it splits into your internal and external carotid arteries in your neck. And then you have baroreceptors located in the aorta, in the aortic arch. Now, both of these are very important, but the baroreceptors in the aortic arch are monitoring the pressure coming from the heart, which of course is very important. But sometimes the pressure in the heart is just fine, but we're still having blood pressure issues. So we also want to monitor here in the carotid sinus, which is particularly important because this is the blood pressure going to the brain. Okay. Now, if blood pressure falls, the baroreceptors accelerate heart rate, increase force of contraction, and promote vasoconstriction. But if the blood pressure is too high, the opposite occurs. Now remember, baroreceptors are constantly active. Okay, but their activity level will increase or decrease depending on what they're trying to signal. So constantly active, let's say at a rate of 10 APs a minute. I'm just throwing numbers out here. These are not real values. But 10 APs a minute to the cardiovascular center equals normal. Now, if we increase to 15 APs per minute to this cardiovascular, this means high blood pressure, because we've increased the frequency. Whereas 5 APs a minute to the cardiovascular center means low blood pressure, as we've decreased the frequency. Again, this allows for one receptor type to signal both high and low problems. This is demonstrated here with these two diagrams. Note, this one here is from your book. This one over here I manipulated to show increasing blood pressure, whereas this one over here shows decreasing. So this one does not exist in your book. I did create it. So if you're not printing out the PowerPoints, realize this one over here won't be in your book. You will have to get access to it that way. Okay. Syncope is the result is basically fainting. I do expect you to read through this on your own and be familiar with it. The question, though, I want you guys kind of to be familiar with is, why do you faint? Well, you faint because your brain's not getting enough blood. And if you think about it, what is the number one thing that's keeping blood from getting to your brain? Well, gravity. What's the easiest way to fix that problem? Lay down. Well, if you are having a lack of blood flow to your brain and you're not responding to the symptoms, well, your body's going to make you respond to the symptoms and force you to lay down with fainting. And of course, there are a variety of different things here that can cause the syncope and the fainting, and I do want you to be familiar with that. Here's an overview of the chemoreceptor reflex that causes the changes in the cardiovascular center. Realize that the chemoreceptor reflex, being that it's monitoring O2, CO2, and pH, well, these things can't be fixed by blood vessels alone. This has to be fixed in conjunction with the respiratory system. And we can make changes to the cardiovascular system to circulate this blood to and from the respiratory system more quickly in order to make those adjustments. But unless we also make changes to our breathing rates, we're not going to be able to adequately deal with the situation. So it's note that it's important that in addition to making these changes to the cardiovascular system, that we also make respiratory changes as well. Last but not least, before we get on to the last topic, we also have a variety of hormones that can regulate blood pressure. This should be a review because, you just took a test on this. And remember, I said these 3 A's would all be coming back up again. Okay? And hopefully you, if you didn't believe me before, you do now. Well, remember, we have, in terms of the effects of renin-angiotensin aldosterone on blood pressure. Well, remember, we have angiotensin 2, which is a vasoconstrictor. Okay, which will increase blood pressure. And then we have aldosterone, which functions to increase sodium reabsorption. All this is at the kidneys. Increase potassium excretion. Okay. Now, because we're doing this results in H2O reabsorption, which leads to an increase in blood volume and an increase in blood pressure. Epinephrine and norepinephrine are going to increase heart rate and cause vasoconstriction, which of course will increase blood pressure. ADH will affect blood pressure by causing, number 1, vasoconstriction. I'm going to just write vaso-C because I'm tired of writing that out over and over again. Number 2, decrease sweating. This decrease in sweating equals an increase in blood volume and an increase in blood pressure. And finally, number 3, increase water at the kidneys, which increases blood volume and increases blood pressure. Finally, we have atrial natriuretic peptide. This guy, of course, is an aldosterone, which means it's going to do the opposite. It's going to decrease sodium reabsorption, decrease potassium excretion. Now, because it's decreasing sodium reabsorption, it decreases water retention, which will decrease blood volume and decrease blood pressure. Okay, so that was a quick review. Well, the last thing we need to talk about is local regulation of blood pressure. Here's the thing. we've been talking about these system-wide methods of regulating blood pressure, but blood pressure and blood flow relates directly back to what specific tissues need. And sometimes what one tissue needs is not necessarily what the entire body needs. So how can we adjust blood flow to a specific tissue based on what it needs? Well, we can't really rely on the nervous system and the endocrine system to do this because their signals are sent out system-wide. But if we only need to increase blood flow to, say, our hand because we're doing a lot of writing, well, we can't really rely on this nervous system to do this because it's going to send signals everywhere. Same with hormones. So how can we locally regulate blood flow and only send blood to those areas that is necessary? Well, this is described by local regulation of blood pressure or auto-regulation of blood pressure. And this describes what is referred to as a tissue's ability to automatically adjust its own blood flow to match its metabolic needs. So let's take a look at how this works. So, I always love to ask this question. Why do tissues need blood? Number one answer, to live. Yeah, no. Okay. We need to be a little more specific than that. We're becoming more and more knowledgeable about anatomy and physiology, and we really need to know be a little more technical in our discussion of that. Well, hopefully, beyond needing to live, you guys realize that tissues need constant blood flow because from minute to minute, second to second, they need a constant supply of oxygen. So then I ask, well, why do tissues need oxygen? Again, most people say, to live. Well, what do they use oxygen for? Well, as you remember from general biology, O2 supply is directly related to ATP production. Well, as you recall, ATP is produced from aerobic cellular respiration, where we take our oxygen plus, hopefully you're thinking, glucose, and we react it to form our ATP. But in addition to ATP, remember we're also producing CO2, H2O, and heat. Well, our O2 supply is going to be directly related to our ATP production. So, if we make this analogy, we can say the more ATP being made, the more oxygen we need. Well, the more oxygen a tissue needs, the more blood it needs. Well, the more blood it needs, we need to increase blood flow. BF meaning blood flow. Well, the best way to increase blood flow is to vasodilate. So the question becomes, how can we get vasodilate from more ATP? Well, we can't measure ATP as our way of increasing or decreasing blood flow because it disappears so quickly. But remember, at the same time we're making ATP, we're also making more CO2, are we not? We're also making more heat. As you'll learn shortly, CO2 is quickly converted to carbonic acid. In addition, if you don't have enough CO2, if you don't have enough oxygen, your body also switches to making lactic acid. So anytime you have acid building up, it means we need more ATP. Well, all of these things, an increase in CO2 concentrations, square brackets around something mean concentration. So next we have an increase in the hydrogen ion concentration, which remember, the more hydrogen ions you have, the lower the pH. Finally, the increase in temperature. All of these things mean that we're making more ATP. Well, if we're making more ATP, then we need more oxygen. We better increase blood flow, which equals vasodilate. Okay. Now, the three main ones that are easy to see as far as local regulators of blood vessel diameter are these guys here. But there is one other one. It's not quite as intuitive, but hopefully it'll make sense. So let's write that one here. The last thing that can ultimately regulate blood vessel diameter is an increase in extracellular fluid, ECF, potassium concentration. Well, hopefully you remember back from AMP1, potassium normally doesn't belong in the extracellular fluid. Well, if it's showing up in the extracellular fluid, that must mean the cell is doing a lot of repolarizing. Since potassium only normally leaves the cell during repolarization, if it's building up in the extracellular fluid, there must be increased repolarization. Well, increased repolarization means that there's increased overall action potential. Well, if the cell is responding to a lot of action potentials, that must mean it's increasing its workload. Well, if you're increasing your workload, then you need more ATP, and we're right back at where we were down here. Increase in, increase action potential, increase ATP. There we go. Well, that means we need more oxygen. We need to increase our blood flow, which means we need to vasodilate. So, a few more steps involved, but it all comes back into measuring the tissue's workload and ATP demand and translating that into an oxygen demand. So this is what we're talking about when we talk about local regulation of blood vessel diameter. This is extremely important as it can adjust blood flow to only the tissues that need it. In fact, local or auto regulation of blood vessel diameter and blood pressure will always override both neural and hormonal signaling. This becomes important because if you think about it, particularly for sympathetic signaling, not all fight or flight responses are the same. If we want to do a very simplistic, demonstration, think about the blood flow necessary for running from a bear versus the blood flow necessary for swimming from a shark. Well, if we're running from a bear, we want blood flow heading to our legs. But if we're swimming from a shark, then we want blood flow heading to our arms and our legs. So how can we direct blood flow in those two different scenarios with one single response? Well, we can't. But what we can do is simply send out signals to everything in the body and direct blood flow away from all areas. If we direct blood flow away from all areas and then rely on the fact that local regulation will increase blood flow to only those areas that are making the ATP because you're running from the bear with your legs versus making the ATP in your arms and your legs when you're swimming from the shark, that allows us to have more direct control and only send blood flow to the tissues that are demanding it. So let's see what we get. Increased activation of baroreceptors. So as you think about these questions, pause if you're not sure the answer, if you need to think about it before I give it to you. Note the double asterisks, so this has two or more potential answers. So increased activation of baroreceptors indicates high blood pressure, indicates low blood pressure, would result in vasodilation, would result in vasoconstriction. Well, increased activation of vasoreceptors. So they're sending signals at a faster rate. Well, faster rate indicates high blood pressure. And if we have high blood pressure, we better dilate in order to bring it down lower. Okay, that's wrong. I think I changed this question and forgot to change the answers. So let me fix that for you real quick. Okay, so here we have our correct answers. Sorry about that, folks. So again, increased activation of baroreceptors. If they're activating more frequently, that means high blood pressure. And if we have higher blood pressure, we want to send out dilation in order to fix the problem. Next question. Now, I just double-checked these to make sure I didn't have any more stupid mistakes. So let's go ahead and try this one out. Which of the following would result in lower blood pressure? ADH, epinephrine, norepinephrine, aldosterone, or ANP? Well, hopefully you recall, since this is all review and you should already have this memorized, the only one of these three, or these four, that causes a drop in blood pressure is atrial natriuretic peptide, or ANP. Last but not least, blank leads to vasodilation. Remembering, we want to vasodilate based on what we just went through. We want to vasodilate in order to increase blood flow, and we want to increase blood flow because tissue needs more oxygen to make ATP. So that means, which one of these four is telling you that the tissue is making more ATP and needs more oxygen? Well, if the tissue is colder, is it making more ATP? Well, if the tissue has extra oxygen, do we need to give it more? If there's a decrease in tissue pH, well, remember, a decrease in tissue pH means increase in hydrogen ion and equals more acidic. Finally, if we're making less CO2, does that mean we're making more ATP? Well, hopefully after looking at it from that angle, you realize the only correct answer is C. Because if your pH is going down, that means you're becoming more acidic. More acidic means you're making more CO2 and or lactic acid, which both would mean we need more O2 and we need to vasodilate. Finally, the last thing for blood vessels that I do want you to read through and look on your own is shock. And you might ask, why am I giving you shock as an independent study? Well, just like I gave you independent study for general adaptation syndrome and stress response in Chapter 18, I'm doing the same thing here for shock and homeostasis, because shock ultimately boils down to a drop in blood pressure. And yet, what did we just spend the last hour talking about? How we regulate blood pressure. So here you're just applying those concepts to a specific scenario of shock. And I've left the slides here that I normally talk about so you can go through them on your own and read them along with reading them in your book. So that is it for Chapter 21. I will see you back again when we start Chapter 19.